All right, so today we're going to start talking about the mole. How many people have heard of the mole? A few people. There's actually an International Mole Day that's celebrated every year. But really all a mole is a counting tool that chemists use, and I like to call it the chemist's dozen. So bakers really like to count in dozens, right? Because it just makes counting a large amount of baked goods easier if you're counting them in dozens rather than individual items. Chemists use Avogadro's number for the same purpose. They use it for counting. So it's a tool used for counting. And it's a very specific number. 1 mole is equal to 6.022 times 10 to the 23rd things. It doesn't matter what things you're counting, just like a dozen. It doesn't matter if it's a dozen eggs or a dozen donuts or a dozen loaves of bread. It's just a counting tool, right? So 1 mole is an incredibly large number of things. To put it into perspective, I've got a few images here. If you take a mole of baseballs, that's about the same as the mass of planet Earth. So it's a large amount of baseballs. If you think about a mole of drops of water, that's the mass of all of our oceans. So it's an incredibly large number. And the reason we use this number is because when we're thinking about chemicals, they're so tiny, we have to think about them being very, very large. So if you think about a drop of water, there's billions of water molecules in there. All right, so let's do some practice. And we're going to do a little bit of unit conversion. So for warm-up, we're going to do unit conversion. And what I want us to do is convert the number of people on Earth into moles. So how many moles of people are on Earth? Does anybody know the rough population of Earth? About 7 billion. I looked it up. This is probably out of date, but we're just going to throw it out here. 7,311,278 is the current population. So now we need to convert that population to moles. So I'll give you a minute to work on this. All right, let's see a show of thumbs. Who thinks they got it? A few people. All right. Let's try it. So anytime you're doing unit conversions, you always start out with what you know, right? So we know the population is 7,311,278,000 people. On Earth, and we want to get rid of people. So I'll put people on the bottom. And we want 1 mole on the top. It's important to remember that 1 mole, moles should be on top. We know that 1 mole is equal to 6.022 times 10 to the 23rd anything, right? Doesn't matter if it's people, tomatoes, apples, watermelon, atoms, molecules. It just needs to be something that you can count, right? So during this unit conversion, we're going to be canceling out the things, which in this case is people, and we'll be left with our units of moles. So if we plug this into my calculator, I'm getting 1.214094653 times 10 to the negative 14th moles. Is that our final correct answer? No, we do need to keep track of sig figs. And in this case, this is an approximate number. So this is 4 sig figs. It is a measured number. That means our final answer also needs to contain 4 sig figs as well. So this is 1.214 times 10 to the negative 14th moles. And that would be our final answer because we do want this to have the appropriate number of sig figs. That is something that confuses people. The mole is a measured value, so you do need to keep track of the number of sig figs that you have in that conversion. Yep?
What is it based on? Like what is it? How do they determine that?
That's a good question. So we'll get into that in a bit, but 1 mole of carbon-12 atoms is exactly 12 grams, and so they've related it that way. So carbon-12 is the standard in chemistry for determining mass. Yeah. All right, so now what we need to do is relate this more to chemistry rather than people, because we don't really do this sort of stuff in chemistry. So in order to convert moles, we need to first know something called molar mass. And molar mass is used commonly in chemistry. It's the mass in grams of 1 mole of an atom or compound / molecule. The interesting thing with this is you can pretty quickly calculate molar mass by looking at the periodic table. If you look at the periodic table, you see the numbers on the very bottom with the decimal points. That helps you determine the actual mass. That's the mass of each element in atomic mass units, which corresponds to the grams per mole. So let's write that down. It's the same as the AMU mass on the periodic table. And so let's take a few examples. The molar mass of helium. If we think about the periodic table, we can look over, is it going to be the 2 number or is it going to be the 4.003? What do you think? Yeah, it's going to be the one with decimals, right? What does the 2 represent for helium? Yeah, how many protons it has or the atomic number. That's different than mass. Mass is going to be the one with the decimals on it. So for example, the molar mass of helium is going to be 4.003 grams of helium for every 1 mole of helium. So that would be the molar mass conversion that we could pull up from the periodic table. Let's do another one really quick. Molar mass of Fe. Does anybody remember what Fe is? It's iron. So if we look at the periodic table, iron is atomic number 26. The mass is 55.84. So it'd be 55.84 grams of iron per 1 mole of iron. Sounds like they're having fun next door. Does that make sense? So use the periodic table as a guide whenever you're looking up the molar mass of individual elements. We do have to take this a bit further if we're looking at a compound or a molecule. So let's take a look at how we do this for compounds or molecules. I wonder what class that is. Holy cow. It's like there's a TV in here. All right, so molar mass of a compound or a molecule is the sum of all the masses. So I'll just abbreviate compound as CMPD. Sum of the masses for each element. So let's do a couple example ones. And for the first example, I'm going to do CaCl2. What's the name of this? Calcium chloride, right? We don't need mono, di, tri, tetra. We also don't need Roman numerals because it's not a transition metal. So this is calcium chloride. Let's determine the molar mass for calcium chloride. And so in order to do this, I break it into 2 pieces. Let's say, all right, we've got 1 calcium. And calcium, if we look at the periodic table, is 40.08. So I would plug that in. And then we've got 2 chlorines. So I'd say, all right, each of those chlorines has a mass of 35.45. And then once you figure both of these out, add them together. And this works out to be 110.98 grams of calcium chloride per 1 mole of calcium chloride. And this can be really handy because now we can create our own conversion factors by looking directly at the periodic table and convert from grams to moles or moles to grams. Let's do another more challenging one. This time I want you to check your work with a neighbor. This is one that's common in biology. It's glucose, C6H12O6. And I want you to see if you can get the correct answer and check with your neighbor. All right, show of thumbs if you're agreeing with your neighbor or you feel confident. All right, it looks like most people are there. So really quickly, let's just break this down. We know we've got 6 carbons, so I'd say each of those carbons is 12.01. We've got 12 hydrogens, and each hydrogen, whoops, that should be a times, not a plus, is 1.008. And then last but not least, we've got our oxygens, where we've got 6 of them, and oxygens are about 16.00, which gives me a net of 180.16 grams of C6H12O6 per 1 mole of C6H12O6. Does that make sense? If you remember too, because we're adding each of these, we need to have the least precise measurement be the last decimal point shown or the last digit shown. So for example, this is only accurate to the hundredths place, where this one's accurate to the thousandths place. That means our final answer can only be accurate to the hundredths place too. So try to remember your sig fig rules even when you're doing this. Yep.
Periodic table I was looking at had carbon as 12.009.
Yeah, whichever numbers you're using, just make sure you use appropriate number of sig figs for your final answer. There are some periodic tables that go out even further.
Right.
Just be consistent.
Okay,
Yeah.
so like 2.
Yeah. Exactly. Just follow the sig fig rules given the numbers that you start with. Yeah. Yep. All right. So now what we need to do is a bunch of math practice going back and forth from grams to moles and moles to grams and whatnot. So I've got a few problems I want us to work on. We're going to do first a mass to mole conversion. And I would like you to try to do this on your own first, and then check with the neighbor and see if you agree. So how many moles of W? Does anybody know what W is on the periodic table? Tungsten, because that makes sense. Tungsten is a filament in the old light bulbs. I think the old Latin name was wolfram, and today we just call it tungsten. So it's present in 9.25 grams of tungsten. That'll be your first one, and then for your second one, I'm going to give you a slightly harder one. How many moles of calcium chloride are present in 5.44 grams of calcium chloride? I'll give you a minute to work on this, but check with your neighbor and see if you agree. I will give you a hint for the calcium chloride. We just did that. So the molecular weight or molar mass of calcium chloride, we said was going to be 1 calcium atom, which was 40.078 plus 2 chlorines, which was 2 times 35.453, which we already said was going to be 110.98 grams per mole. So you can use that. You got to make sure you set it right side up or upside down in the appropriate manner so that you cancel units. That's the big hurdle with this, is people forget that they need to cancel units and oftentimes put the wrong number in the wrong spot. So they'll put the Avogadro's number maybe in the denominator when it should be in the numerator, or vice versa. So let's try to figure out what's going on here. All right, so let's try to do this as a class. We'll do the first one with tungsten, and then we'll do the calcium chloride one next. Like I said, always start out with what you know. So in this problem, we know that we have 9.25 grams of tungsten. So I'll write that out. If we go ahead and try to do our canceling, should grams go on the top or bottom? Bottom. We want to cancel out grams of tungsten. And we want to figure out how many moles there are. So that should go on top. Now the question is, all right, what number goes on the top and what number goes on the bottom? So we need to look at the periodic table to find that gram to mole ratio, right? So if we look at tungsten on the periodic table, it is atomic number 74. It's 183.8. So should the 183.8 go on the top or the bottom? On the bottom. It tells you how many grams there are per mole, right? So I'm going to plug it in on the bottom. So 183.8 grams for every 1 mole. We're going to cancel out grams of tungsten, and we'll be left with our desired unit of moles of tungsten, which if we plug this in, should give us a value of 0.0503 moles of tungsten. And that would be our final answer. And it is important to remember sig figs. Have 3 sig figs going in. That's the fewest number. That means our final answer should only have 3 sig figs. All right, more challenging one. So calcium chloride. So again, we start out with what we know. We know we have 5.44 grams of calcium chloride. We want to cancel out grams, so it goes on the bottom just like before. And we want moles of calcium chloride. And up here, we already figured out the molecular weight on the previous slide, or previous page. So it's 110.98 grams of calcium chloride per mole. So does that mean I put the 110.98 on the top? Or the bottom? On the bottom, right? It's really important that that large number gets coupled with the grams because it's the grams per mole. So it should be 110.98 grams for every 1 mole. And our final answer should contain 3 sig figs. So it should be 0.0490 moles of calcium chloride. And that would be our final answer there. Does that make sense? A lot of it's kind of tedious, just unit conversions, but it's really important that you set up your unit conversions correctly. All right, let's do really quickly. We'll go moles to mass, kind of the backward one. Yep.
I was wondering why it would be 3 sig figs.
Yeah, that's a great question. So the question was about sig figs. Here we've got 3 sig figs. Here we have 5 sig figs. That means our final answer can only have 3, right? If we look at our final answer, do we count that 0? Yeah, it's to the right of a decimal. You count zeros as long as they're to the far right of a decimal. You don't count leading zeros or zeros to the right if there's no decimal. Yeah. Good question. So this one, you want to count all 3 of these as significant. You don't count any of the leading zeros as significant. All right, let's do moles to mass now. So what is the mass of 3.79 moles of Xe, which is xenon? That'll be our first one. And then the second one will be a little bit harder. What is the mass of 0.467 moles of glucose, which if you remember is C6H12O6, and we figured that out previously in our notes, so you might need to use that value. All right, so let's go ahead and jump into this first one with xenon. So if we look at this one, we're going to start out with what we know, which is we have 3.79 moles of xenon. We want to cancel out moles of xenon, so I'll put that on the bottom. And we know we can convert moles to grams really easily, so I'll put grams of xenon on top. Now the question is, what number goes where for this unit conversion? We've got our numerator value and our denominator value. That's a messy E. If you look at the periodic table, xenon's number 54, so the mass is 131.3. Does that go on top or bottom? Top. So it'd be 131.3 grams per every 1 mole. Now we've canceled out moles of xenon. We're left with grams of xenon. And when I plug this in, I'm getting 497 grams of xenon. Is that what you guys are getting? Yep. All right. That's good. Let's do the next one. We know we're starting out with 0.467 grams of glucose, which is C6H12O6. We want to cancel out, oops, sorry, that should be moles. Hurrying here. 0.467 moles of glucose. That means moles of glucose should be on the bottom. And grams of glucose should be on the top. And we know that the 180.16 should go with the grams. We saw that from our unit conversion. So just like before, we're going to cancel out moles, and we'll be left with grams, which for this one is giving me a final answer of 84.1 grams of glucose, which is C6H12O6. One thing I really try to emphasize anytime I do unit conversions is always, always, always show your units. If you don't show your units, it's really easy to get lost. So just make it a habit of showing as many of your units as possible. Don't try to shortcut it. If you leave out, let's say, your glucose designator, you might forget which part of the chemical equation you're talking about. All right, so now let's switch gears and use a different conversion. So now we're going to go from atoms or molecules to mole. So let's do this one first. How many moles are present if you have 3.46 times 10 to the 22 atoms of calcium? I'll just get this symbol here. So that'll be the first one. And then I'll do the next one underneath it. How many moles of PCl5 are present if you have 6.52 times 10 to the 24th molecules of PCl5. let's try doing these as a class. So we'll start with the first one. And in the first one, it says that we have 3.46 times 10 to the 22 atoms of calcium. We want to get rid of atoms of calcium. So I'm going to put that on the bottom so that it cancels. And our goal is to get to moles. So I'm going to put moles of calcium on the top. Now the question is, well, what goes where on the numerator and denominator? And do we need to use the periodic table masses here? No, we don't need to use masses here because there's no mass unit, right? Masses are only used if you've got a gram unit somewhere. So what number should we plug in where? Got to use that Avogadro's number of 6.022 times 10 to the 23rd, but will it go on top or on bottom? Should go on the bottom, right? Because we know that it's defining 1 mole. So 1 mole is always going to be 6.022 times 10 to the 23rd things, right? And in this case, the thing is atoms of calcium. So we're going to cancel that out, be left with moles of calcium, which in this case, I'm assuming my math is correct in my notes, is 0.0575 moles of calcium. Is that what everyone else got? Yep. Yes or no? What did you get? Am I doing this wrong? That's what you got? One of the big things I will say is it's common that people mess these up simply because of calculator mistakes. So one trick I always remind students to do with their calculator, put parentheses around this when you plug it in, and then when you do your conversion, put parentheses around Avogadro's number too. That prevents it from messing up as much when you're typing it into your calculator. When I grade exams and things like that, I really want you to show your work. That way, if it is a simple calculator error, you can get majority credit. If you don't show your work, you miss all credit. So please make sure that you show your work when you're doing these. If you are struggling with typing it into your calculator too, check with me or a friend. That way we can confirm that you're typing it in correctly. All right, let's do the next one. The next one, we've got 6.52 times 10 to the 24th molecules of phosphorus pentachloride. I want to cancel out molecules of PCl5 and get to moles of PCl5. And just like before, we want the number of things we're counting, in this case molecules, to have Avogadro's number. So that's going to be 6.022 times 10 to the 23rd. And 1 will go on top. And remember, put parentheses around these. Double check your work really quick. So see if you type it in, if it matches my value. And the value I'm getting is 10.8 moles of PCl5. Is that what everyone's getting in their calculator? If you're not getting that, this would be a good time to check with your neighbor who is getting it and make sure you're typing it in correctly. Thumbs up if your calculator value is right. That's good. Another good word of advice is I've noticed more and more people are using iPhones and things like that to do their math. And then when they get into an exam, they don't know how to use their real calculator. So try to practice on the calculator you use in the exam. All right, we're going to finish off with the challenge one. The challenge one is going to have more than one conversion. We're going to go from mass to moles to atoms. Okay, so for this one, how many atoms of lead, and lead is Pb, are present in 9.25 grams of lead? We are running a little short on time, so I'll try to guide you through this one and we'll do more practice tomorrow. So we always start out with what we know, which is we've got 9.25 grams of lead. We want to get rid of grams, so I'm going to put grams of lead on the bottom. And the only ratio we have for grams right now is grams to moles, right? We can't go grams directly to atoms. So I'm going to put moles of lead on the top. And I'm going to leave the numbers out right now. Whoa. We'll fill in the numbers next. And now we want to cancel out moles of lead. And we want to get to atoms of lead. And now we need to fill in our numbers. So over here, what numbers should go on the top and what should go on the bottom? Atomic number 82 for lead, the mass is 207.2. Does that go on the top or bottom? Bottom. It goes with the mass unit. So 207.2 grams for every 1 mole of a lead atom. All right. And now if we're looking at the next one, we know that Avogadro's number says 1 mole of something is the same as 6.022 times 10 to the 23rd. Set it up correctly, so we cancel out grams of lead, moles of lead, and we're left with atoms of lead as our desired unit. That means our final answer here should be 2.69 times 10 to the 22 atoms of lead. Is that what everybody got? All right, we'll practice more tomorrow. I know this can be kind of overwhelming. And we want to make sure we're good at unit conversions before we start stoichiometry.